In this video, we're going to take a look at de Moivre's theorem. So by using Euler's relation, we can quickly find powers of complex numbers, given that those complex numbers are expressed in mod arg form. So to begin with here, let's just say that we've got r cos theta plus I sin theta all squared. Let's just write that down here. We've got r cos theta plus I sin theta all squared. Okay. Then, rather than writing this in mod arg form, let's write this now in exponential form here. In that case, that would be re to the power of I theta all squared. If we're squaring this here, we can write this now as a product. This would be re to the power of I theta times by itself again. Like so. So in this case now, just applying the properties here for multiplication of exponential form here for complex numbers, and what we're going to get is r squared. We get r squared times e to the power here of I to theta. Okay, and in this case here now, what we've got then is r squared. We've got r squared cos 2 theta plus I sin 2 theta. Okay, this here, e to the power of I 2 theta, is just this here back in mod arg form. Okay, so if we generalize this here, this gives us de Moivre's theorem. So de Moivre's theorem is a generalization of this result. So for any integer m, so let's just write this down here. So for any integer n, if we have r cos theta plus I sin theta, and this is to the power of n here, then this would give us r to the power of m multiplied by cosine n theta plus I sin n theta. Okay, and like we said, this is de Moivre's theorem. Okay, so this is de Moivre's theorem. Write this down here. So this is de Moivre's theorem. And we can prove de Moivre's theorem by using Euler's relation or by proof by induction. Now, I'm not going to do that for this video here today, but you can easily check those proofs out online. Like I said, I will do a separate video for those as well at some point, but I'm not going to cover them in this video. So there we have it. So that's de Moivre's theorem. So that's everything that we need there. And what we're going to do now is just take a look at some practice questions here for de Moivre's theorem. Starting off with question 1 now, where we simply want to express 1 plus I to the power of 3 in the form x plus iy, where x and y belong to the real numbers. So to begin with here, if I take this complex number here, 1 plus I, I'm going to define that as z. So z is equal to 1 plus I. What we're looking for here is z cubed. We want 1 plus I to the power of 3. And we can easily find that power by using de Moivre's theorem. But before we can use de Moivre's theorem, we need to express this complex number here in mod arg form. So for mod arg form, we need two things. We need r, which is the modulus of this complex number here, z. This is the modulus of z, which in this case would be equal to the square root of 1 squared plus 1 squared. Like so. In this case here, we get the square root of 1 plus 1, giving us the square root of 2. We've got r. What we also need now is theta. So theta here is the argument of z. And to find the argument of z here, this would be tan inverse, or arctan, whichever you prefer, of 1 over 1, which would simply be 1. So we've got tan inverse of 1. And tan inverse of 1 here gives us pi over 4. Okay. We've got everything that we need here now for mod arg form for this complex number z. In this case here, then we can express z here as r, which is root 2, times cosine of theta, so cosine of pi over 4, plus I sine, again, of theta here. That would be I sine of pi over 4. Okay? Like we said, what we want here is 1 plus I to the power of 3. So in other words, we want z cubed. So to find z cubed here, we simply apply de Moivre's theorem here. In this case, now what we're going to get here is root 2 to the power of 3. We get root 2 to the power of 3. Now we've got cosine here of pi over 4, but remember we times this now by this power here. That'll be cosine pi over 4 times 3. That would give us cosine of 3 pi over 4. We get cosine of 3 pi over 4. And then we get I sine. And again, this would be 3 pi over 4. Okay. So from here now, we just need to basically evaluate each part here. So root 2 to the power of 3. Well, that's going to be root 2 times root 2, which would be 2. Then we times that by root 2 again. So what we're going to get here for z cubed is 2 root 2. We get 2 root 2 here for this first bracket cubed. So root 2 to the power of 3 is 2 root 2. Then what we've got here is cosine of 3 pi over 4 plus I sine of 3 pi over 4. I won't evaluate those just yet. Let's just write this down again one more time. We can see it in full here. So cosine of 3 pi over 4 plus I sine of 3 pi over 4. Okay. So now, if we evaluate here cosine of 3 pi over 4 and sine of 3 pi over 4 here, well, what we're going to get then, we keep the 2 root 2 here on the outside for now. Got 2 root 2. Cosine of 3 pi over 4, that would give us minus 1 over the square root of 2. Like so there. If we do the same here now for sine, so sine of 3 pi over 4, that would give us positive 1 over the square root of 2. We get plus 1 over square root of 2 I. Don't forget this is with I here. And now to finish with here, this is for z cubed. We just need to multiply through now by this 2 root 2 here on the outside. So therefore, z cubed here, that's going to be 2 root 2 times minus 1 over root 2. You can obviously simplify straight away here. If you struggle to see where basically the terms are going to cancel, just write the expression out in full. So I'm going to get 2 root 2, that'd be minus 2 root 2, sorry, over the square root of 2. And we've got plus here, so again it'd be 2 root 2 over the square root of 2 I. Okay, in this case here, this root 2 here will cancel with this root 2, so we get minus 2. And this root 2 here will cancel with this root 2, so I get plus 2i there. Okay, and there we have it. But in this case here then, so therefore 1 plus I to the power of 3 is equal to minus 2 plus 2i there. Okay, and there we have it. So that's your solution there to question 1. And if we just take a look now at one more question here to finish with, we've been given this complex number z, which is equal to the square root of 2 times cosine of pi over 8 plus I sine pi over 8. And we're asked to find the exact value of z to the power of 8, given our answer in the form a plus ib, where a and b belong to the real numbers. So to begin with here, what I'm going to do is I'm just going to write down this complex number here, z. So z is equal to root 2 times cosine of pi over 8. Cosine of pi over 8 plus I sine of pi over 8. So if we're looking for the exact value here z to the power of 8, we can simply find this here by using de Moivre's theorem. And because this complex number here z is already in mod arg form, then we can go straight away to applying de Moivre's theorem. So here, just making a note, using de Moivre's theorem. Using de Moivre's theorem here. In this case, we're going to get z to the power of 8. We get z to the power of 8. This would be square root of 2 raised to the power of 8 here, because that's our power. Get root 2 power of 8. And then we're going to times this here by cosine of pi over 8. And remember, we times the argument here by this power. So it's going to be pi over 8 times 8, which would simply be pi. So we get cosine of pi. We get cosine of pi. And then we do the same here with I sine pi over 8. So obviously we times the argument here again by 8. And in that case, we simply get I sine pi as well. I sine pi there. So now if we evaluate this here as we go along, obviously we've still got z to the power of 8. So the square root of 2 to the power of 8, you could just put that into your calculator here. That would be 16. We get 16 times, so cosine of pi here, again, either you already know the exact value here, or you can just put it into your calculator if you're not too sure. That would be minus 1. We get minus 1 there. And sine pi, again, either knowing your exact values, or just put it into your calculator, that would give you 0. Okay, I get minus 1 plus 0 here, so it's just going to be 16 times minus 1. And in that case then, you simply get that z to the power of 8 is simply minus 16 there. Okay, 16 times minus 1 would give me minus 16. And there we have it. So that's our solution to the second question there, question 2. That brings the end of this video on de Moivre's theorem. In the next video, we're going to take a look at using de Moivre's theorem to derive trig identities.